Right. Today we want to talk about organophosphates. I know we have talked about some of these issues. So I will just highlight a few things concerning organophosphates. Then after that, I will talk slightly about some mode of action concerning the fungicides. There's not going to be much actually this afternoon. So let me start sharing. So I will just highlight a few things concerning organophosphate insecticides. Now, organophosphates were developed as navy gases during the Second World War. I've talked about this. This is the structure of the organophosphate. We have got a central P in the molecule, and we have got the either methyl represented by R1 or ethyl represented by R2. So an ethyl group via the oxygen atom is attached to phosphate. Then the Y is either oxygen or sulfur, and the X is a specific organic group, normally referred to as the living group. So here we've got the structure where we now have in this case, the methyl groups attached to phosphorus, which can either be attached to oxygen or sulfur. And we have this other group. So these are the organophosphates. The two other groups are usually the methyl or ethyl and are the same in one molecule. Like this, you can see these are the same in one molecule. X is a complex aliphatic. Usually it's referred to as the living group. We can have this structure POX or PSX, depending whether we have got oxygen or sulfur. So the first group of organophosphates are known as orthophosphates. They have the oxygen here. We have got 4 organophosphates with this structure. The chlorvinphos, dichlorphos, mevinphos, phosphamidone. Then we have got the thione phosphates. The thione phosphates or the phosphorothionettes. Phosphorothionettes. Because we now have a sulfur here. We have got this bromophos, diazinon, phenitrophthione, parathione, then primiphos, methyl or ethyl. Now I want you to check on this one. Here we can have oxygen, but also sulfur here. If we have such a a group. This is when we have thiophosphates, or phosphorothioates, phosphorothioates. And in this group, we have got dimethyl S-methyl, oxydimethyl S-methyl, and the famidothione with this group. And when we have both sulfur, we have got dithiophosphates. Dithiophosphates or phosphorothioates. Phosphorothioates. But probably it's better to call them dithiophosphates. These are some of the products. Some of them are common. Dimethoate, we know it as methyl or dimethoate. Then disulfotone. This one we know it, malathion and menazole. Then we have got the phosphonates. Here we have got the living group near phosphorus. And we have got these two, trichorophone and the butyronate. And lastly, we have got the pyrophosphoramide. Pyrophosphoramide, Shradan, is one of the products. We have got enzymes which attack organophosphates. Some of them we talked about them. The phosphatases type A esterase, microsomal monooxygenase, or cytochrome P450 if you want. Then we have got the carboxyl esterase, glutathione S RR transferase, glutathione S arucyl transferase. Here we have got a typical structure of the organophosphate. Now, if we have this oxygen here, a simple phosphatase can break it through here. Or we can have cytochrome P450 or microsomal monooxygenase enzyme attacking sulfur. And on this bond here, we can have glutathione S-aryl transferase breaking this bond. Or we could simply have a phosphatase breaking this bond. Or it could be a microsomal monooxygenase. Here we can have a glutathione S-aryl transferase. It can also act here. So you can see that organophosphates are prone to a number of enzymes. Again, here we could have discussed it. We have got microsomal monooxygenase, which can affect the ethyl group. We can have carboxylase esterase, which can also This S can be removed by microsomal monooxygenase. We have got this amide, which can be affected by microsomal monooxygenase or carboxylamidase. It can affect this. Now, the practical uses of organophosphates is that these are widely used to control insect pests. They have tended to replace organochlorines, which were quite popular because of persistent problems and the pollution, for example, DDT. Although organochlorines were widely used, because of their persistence in the environment, they are now replaced by organophosphates. But organophosphates require frequent sprays during the course of the growing season. These organophosphates are very effective on aphids. Now, these are the things which we may want to talk about now. We can divide them into subgroups. We've got subgroup 1, organophosphates. These are compounds of low chemical stability. They are soluble in water, but more or less hydrolyzed by it. Water can actually break some of these organophosphates. They are used as contact insecticides, those which are in subgroup 1 organophosphates. Examples are Mavinphos, tetraethyl pyrophosphate, and tetradiclovinphos. So these are the examples. Maybe you remember Mavinphos in subgroup 1 organophosphates. Then subgroup 2 organophosphates, these have got moderate to high chemical stability, but usually low solubility in water, but these are soluble in oil. They are persistent contact or quasi-systemic. They are mainly contact, but they can also enter a little bit into the insect. These are activated before they reach the site of action. Examples of such organophosphates, we have got the malathion, diazinon, phenitrathion, and triclophon. So these are the subgroup 2. Then we have got the subgroup 3 organophosphates. These are of moderate to high chemical stability, activated before they reach the site of action. Now, examples, we have got rogo dimethoate, dimetone methyl, we have got folate, we have got formathion, and disulfoton. Then subgroup 4 organophosphates. These have got sufficiently high vapor pressure, low chemical stability, cyclovos and sulfotep. The other subgroup, which is 5 organophosphates, these ones we can use them as granules for soil application. Examples are chlorvavin-phos, folate, diazinon, and the bromophos. So there's a lot of flexibility on the organophosphates. The last group, the subgroup 6 organophosphates or organophosphorus, these are surface application, systemic action in animals. Examples, we've got fenchclophos, cumaphos, and the dimethate. So these are some of the wide range of organophosphates. We have got various types of these organophosphates, which you may need to pay attention to. So I will stop here on the organophosphates. So I was just going through various issues concerning organophosphates, some of the things which I could have left out, which are important as far as this group of insecticides is concerned. Now I will move on to present a few things about fungicides. Obviously, I'm not going to talk about all the fungicides. There are quite a lot of them. But I just want to emphasize a few things. Now, I would like to indicate that the dithiocarbamates form a group of organic fungicides which are mostly used or which are widely used. We have thiram, which can control botrytis. This is the chemical structure. I just want to talk on the mode of action of the fungicide dithiocarbamate. They say that it has got a bimodal response curve. Now, is increasing amounts of dithiocarbamate, or if you increase dithiocarbamate, at first toxicity is increased with increasing amounts of that pesticide. But there comes a time when that diminishes. And if you continue to increase the rate of dithiocarbamate, it will again peak and start increasing again. And that So most of these fungicides in this group are well known for this bimodal response curve. So if you are increasing the concentration, first there's an increase followed by a decrease and another increase in the inhibition on the growth of probably a fungus. So that characteristic pattern is a kind of their mode of action. Free dithiocarbamates ions are formed within the cells. They can form complex products with heavy metals like copper. They can form these structures. For your own information, the mode of action on most of these fungicides is not a clear story. There are a lot of things which can happen at a cellular level. So I will rather focus on this particular mode of action. It's not as clear as in some of these insecticides and herbicides. Pyrethroids, these are natural products. I'm sure I also talked about the pyrethroids, which come from chrysanthemum species. But we also have fenvarilate, which is a synthesized pyrethroid. And this is the basic structure of these pyrethroids. Probably you may be interested to know the structure. It may be easy to remember it if you focus on this triangle. Here, I'll just mention the mode of action, although I talked about it. Probably it's important to remember that you can have a rapid knockdown effect. As soon as you finish spraying, it tends to kill insect pests very quickly. It is typical of neurotoxic action. Sprayed insects lose coordination and eventually die. What is happening at the nervous system is the alteration of the movement of sodium and potassium. And we can represent the activity of these pyrethroids using these sort of graphs, which indicate the pulses. Or if we record what happens, what goes on in a nerve, the pulse which can move through a nerve, we can get something like this if it is normal. If it is a poisoned nerve, we get this sort of extended. Instead of having one peak, you get an extended peak, which shows disturbance. So that is it on the pyrethroids. So this afternoon's lecture was just probably pointing out some of the issues which I could have missed earlier on the mode of action and some of the details concerning the organophosphates. So I will end it here.